Welcome back to the channel. In the previous episodes, we explored foundation patterns, chain of thought, and tree of thought. But today we step into the world of AI agents. In this episode, we are going to cover ReAct and Reflection. These are two techniques that let LLMs think, act, evaluate themselves, and get better over time. So let's dive in. Let's start with ReAct. ReAct stands for Reasoning plus Acting. It's a powerful technique that guides LLMs to solve complex problems by interleaving step-by-step thoughts, specific actions, and resulting observations, which mimics human problem-solving capabilities. Instead of reasoning in isolation, the model thinks, acts, observes, and thinks again. This was introduced in 2022 and it changed the way LLMs interact with the world. So let's talk about one of the most important papers in agentic AI, which is ReAct, Synergizing Reasoning and Acting in Language Models. Before this paper, language models could reason, but they were disconnected from the real world. They answered questions even when they should have searched, checked, or verified information. What ReAct did was simple but powerful. It forced the model to alternate between thinking and acting. So instead of just producing text, the model follows a loop: thought, action, observation, and thought. This means the model can decide when it needs external information, call a tool, observe a result, and then continue reasoning. This is the foundation of all modern AI agents like LangChain Agents, AutoGPT, GPT-4 tools. They all trace back to this idea. This paper didn't just improve prompting, it changed how we build AI systems. In the paper, ReAct was evaluated on benchmarks like Hotpot QA, which specifically test whether models can reason across multiple pieces of information instead of guessing. They also tested ReAct on AFL World, an interactive environment where agents have to plan, action, and recover from mistakes, not just question answers. Now that we understood ReAct conceptually, let's actually build one using Python and Groq. Okay, so first we import the Groq client and then we set up the API key, which comes from the environment variable. Then we select the model. The model choice in this case doesn't matter conceptually. Any chat capable Groq model works because ReAct is an architecture pattern, not a model feature. Next is the description of the tool. So this is not an executable code. It's just the description. Think of it as a menu. We are telling the model that if you need mathematics, this is what you are allowed to ask. So it has a name, which is calculate, and has a description, which says when to use it. And then the parameters define the JSON schema the model must follow. Okay, now look at the calculate function. This is our tool, the thing ReAct agent can call when it needs reliable math. You can see that it matches with the name. So, allowed is a set, which is a kind of a safety gate, because we are going to use eval and we don't want the user or the model to pass any dangerous Python code. So we only allow the digits, spaces, and basic operations like plus, minus, multiply, divide, decimal points, etc. If any character outside this list appears, we will immediately block it with an error. Then we translate the human-friendly square root to something that Python can understand. We just keep it like this to make the tool interface simple for the model, so it can just ask for square root. Then we use eval to evaluate our expression, but notice we don't use eval dangerously. We pass built-ins, which removes the Python built-in functions. That means the expression can't call things like open or exec or imports, and we only expose one safe module, which is math. We then return the result as a string because tool results are sent back to the model as text. And we wrap the whole thing in try and except, so the tool never crashes the agent. If something goes wrong, like invalid parentheses or something else, we return an error message the model can react to. Finally, available functions is simply a routing table. The model might request a tool by name like calculate, and this dictionary tells our program which Python function to execute. This is what makes the agent extensible. Tomorrow, you can add more tools like search, read file, or query database, and the agent loop stays exactly the same. So calculate is a safe, deterministic tool, and available function is how we map the model's requested action to real code. Next, the function is execute tool call. This is the function which is the bridge between the model and the real world. The model gives us tool name, and arguments, we map that to actual Python code. So we extract the tool name, then look it up in the dictionary, deserialize the JSON arguments, and execute safely. Now comes the system prompt that defines the role of the model. We explicitly define some rules in the system prompt. You can see that if you need math, you must call this tool, never write function tags, use the tool calling interface only, and after receiving tool results, produce the final answer in plain text. Before we go any further, there is one important detail I want to call out. When you build React agents with real tool calling, the system prompt is not optional. If the prompt is too loose, the model may try to invent its own tool syntax like XML style, function tags, etc. So in practice, we explicitly tell the model that do not write function calls manually, use the platform's tool interface only. Next is React agent function. This is our agent. Everything else we wrote above is support code. If you understand this particular loop, you understand how tool using AI agents actually work. So we start by building a message list. Think of this as agent's working memory. The system messages set the rule for the agent and how the agent should behave. And the user message is the task we want to solve. The key idea is that we keep appending to this list so the model can see the full trace of what has happened, thoughts, actions, and observations. So now we enter a React loop. Each iteration represents a thinking cycle that the model thinks, maybe takes an action, observes the result, and then thinks again. We set max steps equal to 6 in this case to prevent infinite loops. Next is we are ask the model that given everything you have seen so far, what do you want to do next? And importantly, we also pass tools. That means the model is allowed to choose between replying normally in text or requesting a tool like calculate in our case. The model doesn't run the tool, it only requests it. Next, we take the model's message and append it to the memory. This is crucial because we are building a transcript of agent's reasoning and actions. So the next model call has context of what it has already tried. Now, next we check whether the model requested a tool. If there is no tool calls, that usually means the model believes it has enough information to answer. So we return the final answer and we are done. If the model did request tools, this is the act part of React. The model gives us the tool name and the argument in JSON. Then our code execute the tool locally by using execute tool call function, which is here. Now this is the observation part. Once it makes calls to execute tool call function, we take the tool output and add it back to the conversation as a tool message. Notice that we are also including a tool call ID that links the observation to exact request the model made. Now when the loop repeats, the model sees the exact observation and can reason from real data instead of guessing. This is where hallucinations drop because the model is now grounded. Finally, if we hit max steps limit, we stop gracefully. This prevents the agent from looping forever if the model gets confused or keep requesting tool. So okay, let's run this function now. Okay, so this line tells us that the agent explicitly called the calculate tool. The tool evaluated the expression for the first question that we asked, which is what is 9 multiplied by 23. These results come from Python, not from the language model guessing. So this is the final result that was returned by the agent for the first question. Now the agent processes the second question, and again we see tool result 51, which confirms the agent called the calculator tool a second time. This proves the agent is consistently deciding when to act instead of guessing. Finally, the agent converts the tool's numeric data into natural language response. The wording here is up to the model. So the output confirms that our React agent is working correctly. The model recognized both tasks as mathematical. It chose to call the calculate tool. The tool executed deterministic code. The agent used the observation to produce the final answer. That's it for React. We are going to cover a second prompting technique, which is reflection in this video. Let's move to that. So reflection is a framework to enforce language-based agents through linguistic feedback. So reflection enables the model to evaluate its own outputs, learn from mistakes, and retry. So the loop is attempt, feedback, reflection, and improved attempt. Reflection was introduced in 2023 by this paper. And it answered a simple question: what if an AI could learn from its own mistakes without retraining? Instead of updating neural network weights, Reflection uses language itself as the learning mechanism. The agent attempts a task, then it evaluates its output, then it writes a reflection explaining what went wrong and how to improve. That reflection is stored in temporary memory and injected into next attempt. This creates a feedback loop where model gets better over time. So this diagram from the paper shows how reflection turns a language model into a self-improving agent. At the core, we still have an actor here, the model that takes action in the environment. It observes the results and also rewards, just like an agent. As the agent acts, each step is recorded in the trajectory in a short-term memory. It records what the agent just tried. Next is evaluator section of the model that looks at the trajectory and asks, did it work? What went wrong? What could be better? That next is the crucial part, which is self-reflection. The model generates a self-reflection, a natural language explanation of its mistakes or strategy to improve. The reflection is stored as experience, which is a long-term memory. On the next attempt, the agent doesn't start from scratch. It conditions its behavior on past reflections. So the key is nothing is retrained, no weights are updated. The agent improves purely through the language itself. So the bottom line is ReAct teaches an agent how to react. Reflection teaches an agent how to learn from failures. So now we start with the basic imports: OS for environment variables, Groq for our LLM client, and we initialize the client using the Groq API key, which comes from the environment, and then we pick up a model. Then we define two roles. This is the key to reflection ideas. We split the model into two roles. One is solver and critic. Solver tries to answer the task and critic reviews the answer and explain what's wrong and how to improve. Same model, but two different instructions. This creates a feedback loop. Then Groq chat function, it's a small wrapper, so we don't repeat boilerplate. It takes a system message and a user prompt and makes one API call and returns the model's text. Then comes reflection function. This function implements the reflection loop. We run multiple attempts here, usually 2 to 5. In this case, we are running 3. We expect the quality to improve each time. So reflection is a list to store the self-feedback. Here starts our reflection loop. This block here is the memory injection. We take last few critiques. In this case, we are taking last 3 and we include them in the next prompt. So this is where the improvement comes from. If you remove this block, the model won't actually learn across attempts. Next, we create solver prompt. Here we have 3 things. First one is task itself, then the past reflections, and then the attempt number. The attempt number is useful psychologically. It nudges the model to treat each run as an iteration. The solver then generates an answer, and then we pass and then we pass the answer to the critic, and we force a structure. The structure is what is wrong, how to improve it, and one concrete change for the next attempt. This structure matters because it prevents vague feedback like be clearer and pushes the model to generate actionable improvements. So next is calling the Groq chat. This is reflection in one line. We take feedback, then we store it as memory. Then in the next attempt, uses the memory to improve. So in the end, we return the latest attempt and as the final output. And next comes the main block. We demo it on a prime check function because it has clear improvement points. So it's going to write a Python function that checks if the number is prime. The function must be correct, efficient, and easy to read. So reflection has room to actually improve the code. Let's take a look at the reflection output from the beginning. Starting from here, the key thing to watch is how the answer changes across attempts. So there are 3 attempts. In the first attempt, the model gives a solid prime checker and the example usage, but the reflection kicks in. Then the model gives explanation and there is a critic that says what's wrong, how to improve, and one concrete change to apply, which is this one. And then the second attempt starts. In the second attempt, you can see the model actually uses the suggestions from critic. Change was add a check at the beginning of isPrime function to ensure the input is a non-negative integer. So you can see that in the beginning we have this that checks whether there is a non-negative number, and then the second attempt critic gives more detail and implement Miller-Rabin primality test for large numbers, which is this one. I don't have much knowledge around this, but based on the suggestion, the attempt 3 had that thing implemented. Before we wrap up this video, I just wanted to show you all the reasoning frameworks that we have gone through, including the ones that we have gone through in the previous episodes. So on the far left, we have chain of thought. This is the simplest and most familiar form of reasoning. The model receives an input, then reasons step by step in a straight line and produce a final result, a final output. There is no branching and there is no alternative, no backtracking. Next is tree of thought. Tree of thought extends chain of thought by asking a simple question: what if there are multiple possible ways to think about this particular problem? Instead of just one line, you can see we have now branches. The model explores multiple reasoning paths in parallel. Some branches lead to dead ends and other continues. Eventually, the best path is selected as the final. ReAct is reason plus action. This is the foundation of modern AI agents. Instead of only thinking, the model now alternates between thought, action, and observation. And action might be calling a search API, running code, or querying a database. And the observation is the result that comes back. ReAct basically allows the model to decide when it doesn't know enough and then it needs to act. The last framework which we just covered is reflection. Reflection answers a different question. What if the AI could learn from its own mistakes? So the model generates a plan, then executes it, evaluates the result, and then store a reflection about what went wrong. That reflection is saved in a memory here and fed into the next attempt. Nothing is retrained, no weights are updated. The model improves purely through the language-based self-feedback. Let's wrap this up. Today we saw two ideas. First one was ReAct. ReAct showed us how an AI can think, decide when to act, call tools, and ground its answers in real computation. That's how we move from chatbots to agents. Reflection showed us something even more powerful, how an AI that can look at its own output and critique itself, remember what went wrong, and improve on the next attempt without any retraining and without any fine-tuning. So that's the wrap of it. If this video helped you understand agentic AI at a deeper level, please like the video. It really helps the channel grow. Please subscribe to the channel for more deep and practical content on prompt engineering, AI agents, and real-world LLM systems. I'll see you in the next video.